Today we will be discussing about chronic penny model, or in short it's also called KP model. This model is basically is based upon electron motion in periodic potential, that is, in a crystal. As it moves, it undergoes certain periodic potential. So how the motion of the electron should be and how it will affect the different zones or different energy levels. So let us first try to understand or try to visualize the periodic potential that we have. So this is a periodic potential, and having the period A, whereas the width of the potential as B. Okay, so from 0 to B it determines the width through which the potential is existing, and the 0 to A is the gap between the different potential. Now these potentials are analogous to the different positive ions present in a crystal. Now the electron is supposed to move through the crystal, so it undergoes this positive ion, so it actually hops around this positive potential, the electron. So how the motion of the electron will be? To understand that, we need to write the Schrödinger's equations for these two cases. One is in the potential, one is outside the potential. So in the potential, that means when the position is between B and 0, we're talking inside the potential, the Schrödinger's equation will be d square psi by dx square plus 2m h cross square E minus V psi is equal to 0. Now that means there is a potential V present, so this potential is basically the V potential we are talking about. And outside the potential, that is when we're talking about between 0 and A, that means this area. So simply V will be, there won't be any V, so 0 to A, the potential is 0, so that makes the equation look like d square psi by dx square plus 2m E by h cross square psi is equal to 0. So these are the two Schrödinger's equations. Now what we assume that the energy of the electron is less than the potential, and we consider two constants. One is called alpha square, which is equal to 2me by h cross square, and beta square, which is equal to 2m by h cross square E minus V. So we end up in the two Schrödinger's equation written as d square psi by dx square plus alpha square psi is equal to 0 for the first case, That means when x is between 0 and a, when there is no b, and the second one is d squared psi by dx square plus, minus square psi is equal to 0, and this is for position inside the potential. And the potential is of course periodic, so it comes back after an interval, so that interval is nothing but a plus b. So this makes Vx is equal to Vx plus a plus b. So the solution of this Schrödinger's equation is something like this: I is equal to uk x e to the power I k x, and this uk is basically, it's a periodic function with the periodicity of the lattice, with periodicity of the lattice, and the periodicity is a plus b, so that is why uk x is equal to uk x plus a plus b, and the probability, if we consider the occupation index Fe, so it will look something like this. And this is your potential. This is one potential. This is another potential, so on and so forth. This is the k value, or the wave vector value. This is Fe, and these two are the maximum values of Fe, that is plus 1 and minus 1. So let me draw them separately. So first draw the potential. So this is the potential. The periodic potential that we talked about, and the value of Fe is actually like this. A little bit like this. Okay, so this is your Fe, and this is your K exponent minus 1, and so this gives you the physically acceptable solutions possible between plus 1 and minus 1. Okay, so let's put it like this: physically acceptable solutions between plus 1 and minus 1, and k here is equal to plus minus pi by a plus b. So it actually tells you about this value or this width, and so using this, if we plot a relationship between the energy and the k, so it takes the shape like this, a discontinuous plot, and these discontinuities are marked by certain values of k. Say the first, this is minus pi by a plus b, and this is pi by a plus b. So a difference of 2 pi by a plus b, and this is where the electron exists, and this is called the first Brillouin zone. Brillouin zone, whatever you may call it. Secondly, we have we have a band gap in between the two zones, and the next zone is between minus 2 pi by a plus b to 2 pi by a plus b. So this width actually increases as we increase the value of k, and if we consider a continuous, we do a convolution and draw a map at different points. So this corresponds to the usual bulk value formula is square k square by 2m is equal to E. Now due to this, so what it actually shows that due to the periodic potential in the crystal, the electronic path is not smooth and it undergoes certain obstructions. Okay, these are of course the band gaps, and it is only allowed to stay in the zones which are called Brillouin zones. So first Brillouin zone is say this one, the second is say this one, and so on and so forth. So we put it in words. So it shows that first of all the band edges can be seen. Okay, so let me draw. Consider one single part. These are the band edges we're talking about, and when we as the value is f is between +1 and -1, so we can put it as cos the periodic potential cos k a plus b. Since this is your solution, so we have a real part which is given as a sine part, and we have got a the imaginary part is sine part, the real part is cos part. So that's how this cos k plus e by 2, this value comes out to be plus minus 1. So this makes it k to be equal to plus minus n pi divided by a plus b. So that's how the value of the Brillouin zone or the allowed region comes. So now as energy tends to infinity, that means for very large values of energy, the EK relation will then follow the normal free electron relationship. It is E is equal to h square k square by 2m. So it means that the effect of the periodic potential is no longer there if we increase the energy of the system. Or we can also see that for large energies, the allowed bands are broad and the forbidden bands they become narrower. So that's how there is a continuous pattern. Now the another case, this is the first case, we call it as case 1. What now there is another case is if the potentials are very deep, that means if the potential wells are very deep, then what do we have? And widely spread. Now, if this is the case, then the electron has not got sufficient energy to hop from different potential to different potential, and then what will happen? The electron will be bound to one of these potentials. So it also indicates that there will be low energy values of the electron, low energy eigenvalues, and so put it like this. First of all, it will imply that low energy eigen values. This is the first implications, and the second one is, and these values will be also nearly equal. The different electrons. The next case is that if so, look at it as case 3. As case 3. Case 3 says that if the wells are close together, that means the gap between the different wells are very small. So wells are close together. And then what will happen? Their levels will spread into energy bands. So this is a very well-known fact that we have different wells. If they come very close together, so there will be a mix-up between the wells, and they will eventually form two separate bands. So this is what is happening here. It will spread into energy bands. Now, as B is reduced, B comes down. That means this is what it actually means by putting the wells close together. So, giving a low value of V will indicate that the resulting bands that are formed, they will be wider. And the last case is case 4, which is saying the opposite. If the value of V is very high, right? V is extremely high. So, and A and B are remaining fixed. So it's like that. If you have a potential like this, now the potential has gone like this. So position of A and B are fixed, but with respect to the potential, the value of A and B are now quite small. So that means the width of the energy band, so it will imply, so it will result into width of the energy band. It will actually decrease, come down. Now, instead of using this scheme or this way of representing the EK diagram in terms of Britton zone, there is another way of representing this. This is called the reduced zone scheme, or you can call it reduced zone representation. So basically it's the same diagram versus U versus K. So instead of showing the Brilliant zones horizontally, we show it actually vertically. So this is the first Brilliant zone between minus by A plus B, and this is also pi by A plus B. So the next Brilliant zone actually starts like this. So this is E and this is your K. So from minus pi by A plus B to pi A plus B. So this is, as I already told, this is the first B zone, and second minus 2 pi A plus B to 2 pi A plus B. This is the second B zone. Now, what we actually do here is in the reduced zone scheme, we replace K by K plus minus 2n pi by A plus B. So even if you replace, the equations still remain the same. And why do we do it? Because K is not uniquely defined and is useful to translate the various segments of the K curve parallel to the K axis. So this is your K axis. So if we could, what we are doing here, we are translating the segments to parallel to the K axis by replacing K by K plus minus 2n pi by A plus B. So this is your reduced zone scheme representation.